Welcome, and today we're going to be studying change of variables in 2D integration. T-I-O-N. Okay, so change of variables in 2D integration. It'd be worth our time to before we start studying in 2D to actually review 1D. So we all know how to do this thing. This is the so-called U substitution. So let's go over that again. So we have some integral from a to b of f of x dx. All right, and that's approximately equal to the sum of f of x of I, where x of I are some representative values, 1 to n, times delta x, which is the width of our partition. And we want to think of this as some function like that, over some interval a to b, and we've broken it up into these partitions, delta x. And there's our x of I, and there's the f of x of I right there. And what we do, of course, is add them all up, and we weight them according to how much of the interval, essentially, is covered by that representative value, and we use that as our approximate integral. So the idea is that sometimes this integral here might be difficult to calculate using the fundamental theorem of calculus. Maybe we don't know the antiderivative of f or something like that. And so what we want to do is do a change of variables. So we say let x be some function g of u, right? And the idea we know and love so much is, let's put a comma there, is to go dx du is equal to g prime of u, and then say that dx is actually equal to g prime of u du. All right, and that means we can go down here like that, integral of f, and then wherever we see an x, we put a gu inside, and then we put a g. Everywhere we see a dx, we can put a g prime u du. And the idea is that this integral is easier to compute. So before we do that, though, we have to also find new limits of integration, which I'm just going to call c and d. So the idea is we have some function, I'm going to call it g of u, right? And that's going to be over some other interval now, c and d. Okay. All right, and they might be completely different values from a and b. The idea is that c should map, you can go in, it'll map to A, and D will map to B. And it could actually be the opposite way. It could be that D maps to A and C maps to D. That's B, that's okay as well. But yeah, we'll just think this is sort of a schematic example. And the idea then is that the delta x's become some different partition. We'll call them delta u. And delta u, of course, is going to be equal to, it'll be equal to delta x over g prime of u. And I'm going to put these delta ui's, I'll make them ui's because the idea is if we have some value, we'll call it ui, that's the one that's going to map to x of I. And the width of that interval, of course, is going to be proportional to delta x, but then we have to divide it by this factor here. Another way to think of it is, of course, g prime of ui is equal to, times delta u is equal to delta x. And you can think of this as sort of the dilation or contraction of the intervals, delta x. All right, so if g prime is big, essentially the delta u's will be smaller than the delta x's because we're going to divide by a big number, and vice versa for small. And the idea is that by doing this, this integral may be easier to compute. And this goes into that whole metaphor that if you're in some world, in a space X, and things are difficult, we may need to transform to a new space, a U space here, and that's X, where by stretching and contracting our X space in some prescribed way, in a sense, the integral becomes easier. And of course, we can go back and forth between these two. If you see this sort of integral, you can always map back to this sort of integral, and vice versa. So, let's give a quick example to make this more relevant. So we have maybe 0 to pi over 2 sine 2x dx. So the idea is if we say let u equal 1/2, let x equals 1/2 u, right? So that's my g of u. And that means my g prime of u is just equal to 1/2. All right? And that means we can do something like this. So we say that we'll change it then. It goes sine, wherever I see a 2x, right? So this is the same thing as saying 2x is equal to u. I can put a u in its place. And then wherever I see a dx, I put 1/2, right? G prime times du. And then all we have to do now is map to a new u space. We got to find our limits of integration. So if I put a 0 in here, I get a 0 out. So that limit doesn't change. But if I put a pi over 2 in, of course that becomes pi. All right. And then this integral becomes much simpler to do, or a little bit simpler at least. I mean, this is a pretty simple example to begin with. So those are equal. And we take the antiderivative, which we know the antiderivative of sine u, 0 to pi, and that becomes 2. Or sorry, 2 over 2 is equal to 1. So there's an example where we use this. So the idea here is then, so what does that represent then? It represents a stretching of the space. So G prime was 2, G prime was 1/2. So you can think of that as a stretching of the X space. We've stretched it out. So it was 0 to pi halves, and then the new domain is 0 to pi. So it's doubly as long. And because we're integrating over a longer space from 0 to pi, a longer length of interval, we need to have all the result that we get out of it. So that's the idea. All right, so now let's go on and talk about 2D integrals. All right, so there's a very similar flavor to it. Again, we have some sort of area integral, f of x comma y over some region, we'll call it R, dA. Okay, so, and that will be, we can think of that as some sort of weird region, call it R, like that. Right, and the idea is that perhaps this function over that particular region is a difficult integral to calculate. We can't find a way to iterate the integral. We can't find a way to make it simple. So what we want to do is find a transformation such that we have find a transformation t u comma v that's in some new space that transforms to x comma y, right? So another way to write this. So I'm gonna and then say that what we want to do then is find some sort of set S, we'll call it S, where we have a map or function, and this is UV space here. It's a different, and it maps to this region R, right? So one way to write that is that it goes from S to R. We want it to be invertible, So we want there to be an inverse. We also want that the t is smooth, invertible. Okay, so smooth just means it has a continuous derivative. Okay, so that's nice. So so one way to write t is to write it. I like to write it in terms of vectors uv, and that's going to be equal to x, y, which I can also call r. Okay, the vector r, and it's going to be some. I'll put it in vector form: g of uv and h of uv, two other functions, g and h, right? So these functions are continuous and smooth, and they're invertible. All right, another way to write them again is g times the unit vector I plus h times the unit vector j. Oh, sorry. H times the unit vector j. Okay, so that's nice. Now, what we want to do then is be able to find a way to do the same thing we did with our change of variables in 1D, is when we change to UV, there might be some dilation of our intervals. So we're going from, so we have some sort of box, let's say, some little area element that's going to be du and, or sorry, delta v and delta u. I'm going to take a point in there. That's our representative point uv, or u0, v0. And that point, I'm going to say, is going to map to some point there, which I'll call x0, y0. Okay? All right. And we'll say this whole box gets mapped to some sort of weird shape. Who knows what it will be, but it might be like this. Like that. And so each corner somehow gets mapped, and this whole thing right here gets mapped to this box here. So two little pieces. So I'm going to bring that out here. I'm going to focus in on that little patch here. And I'm going to say that I want to know what the delta A is for that little patch. And the idea here is that if we keep tiling out this space with little patches, there'll be similar tiles here that will fill out the entire region. So we want to know what this little area element is, and we do it just like before. Again, that was the point. We took that point u0, v0, and we transformed it through this nonlinear function, and that turned to x0, y0, which is also where I'm going to call r, the vector r0. Okay? And if I go in this direction, say, like that way, it's going to send this vector, make a vector, let's say, call it p, that gets to there. I'm going to call that new vector here to be r of u0 plus delta u plus vu, so v0. The same thing here. We have a q vector that's going to start at this point here at r0 and end at a point r u0 v0 plus delta v. Okay? All right. So so I want to know how do we get q. So from p and q we can get an estimate of this delta A interval. So delta A is going to be the magnitude, the vector magnitude of p cross q. Okay? So p cross q is fine, but we got to estimate these what they are. So we've done this before with surface area integrals. So the vector p is going to be r at u0 plus delta u v0 minus r at u0, v0, right? That's this point right here. And that's going to be approximately equal to the u derivative times delta u, okay? Which is going to be, well, what's the u derivative of this function here? Or right here it's going to be I times g u, the partial derivative of g with respect to u, plus j times h u, the partial derivative with respect to of h with respect to u. Likewise, q is going to be equal to r u0 v0 plus delta v minus r u0 v0, which is approximately equal to, this is a linear approximation, we'll call r v, the partial with respect to v, times delta v. Oh, sorry, this needs to be multiplied by delta u. And that is I gv plus j h v, all multiplied by delta v. Okay, so delta a then is going to be equal to ru cross rv times delta u delta v. Because scalars go right through cross products, they pass right through them. So there we go. All right. So so let's take this calculation further. What are we talking about here? So normally when we're talking about a cross product, we're talking about vectors in 3 dimensions. So one way to do this is to just kind of do a little fudge factor here. Put 0 times the k vector. A 2-dimensional vector is really just a redundant 3-dimensional vector. So let's take the cross product here then. So I'm going to multiply my delta u and delta v. They just hang out for a while. And take that vector magnitude. I'm going to do a determinant I, j, k. And again, what we can do is always just put a 0k vector and a 0k vector there. And then what we'll do is, so we're going to take a vector magnitude of a determinant, a cross product, and it'll be gu, hu, gv, hv, 0, 0. And you can do the calculation pretty straightforwardly, that this is going to be delta u, delta v, times the magnitude of the vector. It'll be 0i plus 0j plus the determinant of the submatrix here, which is going to be gu times hv minus gv times hu times k. We're taking the vector magnitude of that, which is straightforwardly delta u, delta v times the absolute value of gu, hv minus gv, hu. All right, so of course you take delta u, delta v closer and closer to 0, and then you get dA is equal to gu, hv minus gv, hu, absolute value, du, dv. Okay, so there's our change of variables formula to find out this. And again, this plays the same role as our g prime of u in 1D intervals, right? So this represented that sort of length distortion of intervals. This represents a volume distortion from our change of variables. So we had some nice little square here in u space, and we mapped it over. It turned it into some sort of funnier space, and the volume will have been sort of expanded or contracted in some way as according to the mapping. So so let's just write this down. I'm going to get a new sheet of paper here. So the idea here is we have some t uv. I'll write out the formula here then. That's going to be equal to x comma y. And what we have is what we call the Jacobian, which is going to be the absolute value of gu. Sorry, that's going to be equal to g uv h uv. That's a vector. And that's going to be gu hv minus gv hu times du d. Sorry, I won't put those there yet. That's what we call the Jacobian, the absolute value of the Jacobian, or the determinant of the Jacobian. It's one way to think about it. So, so we have an integral, and it's going to be over some region R, f of x comma y, dA, and we can write it as the integral over S, some new region, where f is now going to be a function of g u comma v. That's what we replaced x with, right? That became g. And then h u comma v. And then we put our absolute value du hv minus gv hu times du dv. All right. And the idea here is we have some area S, we have a mapping, a transformation T, some sort of nonlinear transformation that's invertible and smooth to some other region R. And this integral, hopefully, is a simpler integral to calculate. So thanks very much. In the next video, we'll actually do an example calculation.